Okay. So, yesterday we are discussing the elements of probability and stochastic process. We went up to correlation, and then we took up discrete random signal, and then for that we discussed what is called stationarity, weights and stationarity, correlation, and then autocorrelation function has one property which is the Hermitian property. That is we defined R k as E of x n x star n minus k. This is just for recalling. Okay, this is what I did. It is a function of what is the lag or the gap k. K is called the lag variable R k, and we found we established this property, Hermitian property. That is R k is same as R minus k star. We proved this yesterday. Okay, it is very easy. And if it is real valued signal, the star has no business, which means R k is just R minus k. It is just an even function. Okay, otherwise it is conjugate symmetric. Another thing is, another property is this R 0, which is E of mod x n square. You understand, if you put k equal to 0, x n x star n, which is mod x n square, this has to be real and non-negative. So, this is this. Okay, this is this. This is what we saw yesterday. Okay. I think yesterday I stopped here only, isn't it? Can you to him? Yeah. Okay. So, I start from here. There are some more properties of this autocorrelation, but that about that, I mean, like there is something called Cauchy-Schwarz inequality and all that I will present later when need arises, not now, because afterwards I will be presenting this entire stochastic process in a vector space framework, geometric framework, and there a lot of things will be very clear from geometric insight, using geometric insight. Okay, so that time I will develop some more properties, especially some particular inequality which is called Cauchy-Schwarz inequality, which is very useful in proving things. Okay, very useful property and key in communication mostly. Okay, so that I will not go into. Now, this R k is a sequence, isn't it? It is not a random sequence. X n is random. The moment you apply E over it, you get a deterministic value. So, R k is a sequence. The moment you have a sequence, you can be tempted to take discrete time Fourier transform DTFT of this. Suppose just we take a DTFT. Okay. So, R k, if you do not know DTFT, those who do not know, they have to read it. I am sorry, it is not a course on course on DSP, so I cannot help that. If you take this discrete time Fourier transform, omega is the digital frequency whose unit is just radian. If you take this, okay, k equal to in general minus infinity to infinity, and even though it is a function of omega, in DSP the style is to write it as a function of just not of omega, but e to the power j omega. That is, we can call it phi, and by the way, okay, phi here, okay, it is all right, phi e to the power j omega, though E is not a variable, j is not a variable, okay, j is not a variable, E is not a variable, actually omega is a variable, but still this is the notation. We write like that, and yeah, like the mobile turned on, I should switch on my mobile too, because that will get recorded. So, just 1 minute, and those who have their mobiles, please. Sorry for this deviation. E is not a constant, j is a constant, but still we write phi e to the power j omega. Actual variable is omega, which is digital frequency, but this is the style. We write it like this just to indicate that phi e to the power j omega is actually a power series in terms of e to the power j omega, which it is. This thing has some nice property. Any DTFT as such, is periodic function of omega over a period 2 pi. So, if you want to plot it, it is enough if you plot it from say 0 to 2 pi or minus pi to pi. Okay, we normally plot it from minus pi up to plus pi, and then that will get repeated. Now, that is common for any DTFT which is valid here also. But what does this give? What is the meaning of this? And what are the properties this has? Let us find out. I have just taken a DTFT. But is it different from, is it something special? Does it have some extra property? And what does it, what is the physical meaning of this particular DTFT? Let us find it out. Now, you know inverse DTFT. If I want to find out R of k given this, there is an inverse DTFT, that is I DTFT is R of k okay, this is standard. So, that means what is R of 0? R of 0 is but what is R of 0? R of 0 is E of mod x n square. Because of stationarity, this quantity does not depend on n. So, at any index n, mod x n square is the instantaneous power for a particular waveform, and if you take expectation, there is an average power, and because of stationarity, that does not depend on the n you chose, everywhere it will be same. So, it is the average sample power, per sample average power. That quantity is what? Is an integral of this DTFT. So, this quantity phi e to the power j omega, what does it indicate? What does it indicate is this, you know, that it kind of gives a distribution of the total power R of naught R 0 over the whole frequency range from minus pi to pi. This gives a distribution. Because you integrate net integral, forget about the 1 by 2 pi scale factor, the net integral gives you this average power. So, this quantity gives a distribution. That means, what is this quantity? If you take a zone from omega and omega plus d omega within that small strip, how much is the power? Phi e to the power j omega into d omega. What is the total power? Integrate. So, that is why it is called power spectral density, PSD, power spectral density. This is called power power spectral density in short PSD. What are the properties? Firstly, periodic in omega over period 2 pi. Okay, that is standard property of any DTFT we know, there is nothing special. But another important thing is, we know that this quantity RK is Hermitian sequence, it satisfies Hermitian property. What does it mean? If you really take this summation, divide into two half, one from say plus 1 to infinity, another say minus 1 to minus infinity, and take R 0 separately, then phi e to the power j omega, it will be what? R 0 into e to the power 0, that is 1, plus 1 will be from k equal to 1 to plus infinity, or k same thing e to the power minus j omega k, another will be from same thing, but k minus 1 to minus infinity. Suppose I am not writing some steps, you here be, suppose in that other summation, instead of k I call it minus k, instead of k replaced by minus k prime. So, that means the summation will be from 1 to infinity, it was minus 1 to minus infinity, k is replaced by minus k prime. So, in terms of k prime, it will be from minus 1 to infinity, that is all. And wherever I have k, that will be replaced by minus k prime, and why again minus k prime, call it minus k. So, put the two things under the same summation, or minus k e to the power plus, because it is already minus here and k is replaced by minus k prime or rather minus k. So, minus plus e to the power j omega k. And what is R minus k? This quantity from the Hermitian property is R star k. From the Hermitian property here, R minus k is R star k. So, if you call this quantity as A, this is A star A, and what is A star? R star k e to the power plus j omega k. So, A and A star when summed is a real quantity. So, it is a real function and R 0 is always real, non negative, but real. So, this is what does it give then? Actually, the summation will be like this, R 0 plus twice real part of R k e to the power minus j omega k. Okay. If R k is real, so it is a real function, mind you, because of the Hermitian symmetry of the autocorrelation sequence, this is a real valued function. And obviously, it should be, because when you integrate you get power. So, power is not complex, it is a real quantity. So, this integral is actually okay, it should be real, it is because integral is giving you real, and now this is a real function we have proved. Whether you have got a complex valued sequence or a real valued sequence, this is a real quantity. Okay, this is proved. Now, for the particular case where x n is a real valued sequence and therefore, autocorrelation function R n also is real valued, there you see the inside quantity real value, real part of R k e to the power minus j omega k. R k can be taken out, R k is real. So, only real part of this stuff e to the power minus j omega k, which is cosine omega k. So, this leads to, if you permit me writing here, if I write, can you see this? If I write something, no. So, can you see this here? So, for real valued signal, sometimes that random signal is called random process. Real valued process means random process, random real valued signal. This will be equal to R 0 plus okay. So, one thing you have seen, there is a real valued function. There is another property we will show, that is actually a non-negative function. It is not only real, it can never become negative. Any point, if you plot it from minus pi to pi, it will never become negative. It is always non-negative. That proof will require some more things. Actually, I am forming some background for taking a plunge into this statistical signal processing or adaptive signal processing course. So, it is just background. Some of these may be familiar with you, but I have to put them in the framework I prefer, okay, because this is, I would say, quite elementary. And for those who are not aware of this, it's, I think it will be a good exercise, good exposure. Now, one thing you see, for the real case, if it was not real, this guy phi e to the power j omega is, I understand, real valued, but phi, if suppose omega is replaced by minus omega, here it will become e to the power plus j omega k, but this entire thing will be a defined quantity again, isn't it? So, that overall function may not have anything to do with, you cannot find out a direct relation between that function and phi to the power j omega, phi to the power plus j omega. But suppose I am dealing with real case, then R k will come out and you have got this formula. In this case, phi e to the power minus j omega, that is at a frequency minus omega, what that will be? This was the same, this was originally, because cosine minus and cosine plus they are same. So, that means for the real case, it is not only a real function, for the real valued signal or real valued process case, power spectral density is not only a real function, it is a function which is even. At omega, whatever is the value, same value you get at minus omega. So, it will be symmetric around the vertical axis. We can also show and we will show that it is a non-negative function, but you have understood the physical significance of this. Suppose you have got a process, you have got a random signal where every pair of every two samples, whether they are adjacent neighbors or they are far away from each other, if there is no correlation, that is suppose special case, suppose R k which is E x n, it is some constant capital N times delta k. It means and I am dealing with zero mean random process, mind you. I am dealing with zero mean, I am always dealing with zero mean process. So, suppose our case like this, what does it mean? When k equal to 0, when k equal to 0, then right hand side is capital N, which means E of mod x n square, there is a variance, is a constant independent of n because of stationarity, and that is equal to capital N. So, capital N is the variance of average power, and otherwise the correlation is 0, isn't it? So, any two samples, whether k equal to 1 or k equal to 1 million, the correlation is 0, and since I am dealing with 0 mean random signals, correlation 0 means they are uncorrelated. I told you yesterday, in general two random variables x and y are uncorrelated if E of x y star is equal to E x into E y star, but when you are dealing with 0 mean case, then E of x, there is mean is 0, E y star is 0. Conversely, for 0 mean case, if E of x y star is given to be 0, you can interpret this way, that E of x y star is indeed equal to E of x into E of y star, because E of x is given to be 0, E of y star is given to be 0. So, you can write it like that, and therefore, it stands to be uncorrelated. This I did yesterday. Okay. So, for a 0 mean random process that has this kind of autocorrelation function, it corresponds to a random process where there is no correlation, 0 correlation between any pair of samples. Only when sample is multiplied by itself, then it becomes variance, it has to have a value capital N, which is non-zero, greater than a positive number. N is a positive integer, positive number, not integer in general. For such case, for such kind of random process, which is actually purely random, absolutely random, no correlation between any two persons, highly random, highly erratic, that is what it means, no correlation, total chaos. For that, what is the power spectral density? If you take the DTFT of this, what do you get? Can you tell me? In the DTFT formula, n into delta k into e to the power minus j omega k summed, but k equal to 0 case only has to be taken. K equal to 0 means e to the power 0, 1, and delta 0 is 1, so n. So, it is a flat thing from minus pi to pi, and therefore, it will continue to be flat. This process is called a white process, white signal or white random process, discrete time white random process. White process comes, as you know, from the white light phenomenon. White light consists of all frequencies, possibly with equal intensity and all. Okay. So, here also it consists of all frequencies. So, that is the reason why they call it white. Okay. This is a special case, but white process means there is no correlation between any pair of samples. Okay. Now, one more thing. Suppose there is a 0 mean, or if it is not 0 mean, for the time being here in this context it is more general. So, it is not 0 mean, there is a random process which is stationary, WSS. So, stationary in mean, stationary in correlation. Mean is independent of the index n, it is everywhere same. Correlation is a function of only on the gap or lag k. That kind of process you are passing through a linear time invariant system. You know, linear time, like FIR filter and all, linear time invariant system of impulse response Hn. In general, I am not saying it is causal or non causal, not important. I am here very general, and you are getting one output Yn. Since input is random, output also is random, isn't it? Question is output also WSS? Number 1. Then number 2, if WSS, then what is its mean? What is its correlation, autocorrelation? Okay, let us examine that. Because adaptive filter will do this could be a filter. So, to find out output statistical property, okay, that is the reason I am doing all this, you know, making a kind of groundwork selectively. So, let us find out first what is Yn, convolution between Xn and Hn. You all know convolution, if not, you have to read yourself, but this is not a DSP course. Convolution, say HR. Normally, you can write it either way, you can write XR Hn minus R summed, or this way, both are same. It is a question of substitution of variable, but always prefer this. For most of your sums, prefer this in the statistical signal processing, not the other way. HR Xn minus R is a more preferred version than XR Hn minus R. For simplification of calculations and ease in calculations, nothing else. Choose this version. That means E of y n. What is E? E of a random variable means you have to multiply by the probability density, integrate. And if the y n is a summation, remember, then summation times a probability density integrate means you can apply the probability density function on each term under summation and integrate. So, that means it is a linear thing. You can go on applying that, I mean taking each term, multiply by the probability density and integrate. So, that means expected value of that term. So, E is a linear operator. E of say x plus y is E of x plus E of y. So, that thing if you apply here, you can push the E operator inside the summation, then it becomes okay. HR is constant. So, first I apply E over this product, but HR is not random. So, H of r can come out. See, E of 2x is 2 into Ex, like that. And what is this guy? This guy is the mean of x independent of n or r because of stationarity, WSS nature of the input. So, this is what mu, you can put a subscript x, mean of x. So, that means what is this summation? So, this is independent of n, constant times the summation, whatever is the value that comes up. So, that means mean of any output sample at any n is a quantity independent of n. So, it is stationary in mean, and if mu x is 0, that is input is a 0 mean process, output also 0 mean. Please remember all this. This will be like every time we will be making use of this even without explicitly mentioning. So, these things should go down in your mind. Okay, these are some basic properties associated with the filtering of random process. Next, let us find out the autocorrelation of the output. Whenever actually you have more than one random signal, when I had only one random signal, I use this notation R k is equal to, say, I said this, isn't it, E of x n x star n minus k and all that I said. But suppose you are dealing with many random signals, then to distinguish you put a subscript here or x x. Why x x? Because autocorrelation means product of one x with another x, x x. In case of mean, you have only one x or x x. Similarly, you can find out R y y, and then there is something called cross correlation R x y, R y x, or in the case of R x y, this is x, this is y, and vice versa. That cross correlation I am not going into, though that is a very important topic, but not related here at the moment. So, I will not say I am not covering the statistical signal processing entire thing. I am only taking things selectively which are useful for adaptive filters. Suppose I want to find out R y y k. So, E is pretty simple. Y n now you replace by a convolution sum, this also you replace by a convolution sum, fine. You write H r, again follow this form, H r x n minus r, not the other one, not x r h n minus r, this form I am telling you. H r x n minus r is the variable, and in this case first y n minus k and star. So, in this case h, do not bring r here, r has been used up in this summation, r is a local variable in this summation. Why use the same index? Because there will be confusion. You can use any other index, isn't it? So, use some other index, say h m. X star n minus k, that is the index. You have to find out y at n minus, sorry, forget the star for the time being. You have to find out y n minus k. So, it will be h m x n minus k minus m. So, n minus k minus m, and now star, so star has come. The star of a product is product of the stars. A B conjugate is A conjugate into B conjugate. So, this product, and then what is the meaning of this kind of summations? You start with a particular r, for that h r into x n minus r, n is your choice from outside,
okay, n is fixed. For that again you choose one m, find out this, another m, find out this, another m, find out this summation, that entire summation multiplied by h r into x n minus r, isn't it? Then again take another r, for that r you find out this product and then hold it, again you evaluate the sum for all m, then multiply, again take another r, that is the meaning of this. And remember that such process can be reversed also. Instead of first taking a particular r and then taking the entire summation over all m, and then again taking another r, again taking this internal summation over all m, I can do the reverse. I can take one m and move over all r, then another m, again move over all r. You will cover all the same points. This is basic thing. Two double summations can be interchanged, and you can extend here discrete summation. If one is integral or both are integral, they also can be interchanged by the same logic. You follow this stuff, this is basic stuff. Okay. Now, E will be working only on not on H, but only on X. That means this X and this X you put together, E applied on this. So, it will become like summation of r minus infinity to infinity H r, just a minute, you have another summation m, same range, into E of this quantity. Okay. Now, what is this? This correlation, autocorrelation of x, but what is the value? This index minus this index, this minus this was the thing, na? You remember? The lag, the gap between the two time points. This is one time point, this is another time point, and n cancels. That is the important thing. The moment n cancels, the entire summation becomes independent of n, which means this RYY this thing, in fact, I shouldn't have written as RYYK. The moment I wrote as RYYK, it gave the implication that the entire thing depends only on k, not on n. So, maybe I shouldn't have written like that, I should have started like this, because without proving stationarity of output, I am using a notation that implies stationarity. So, let us start with this. This thing I was trying to find out. If this depends only on k and not on n, if it is independent of n, then stationary in correlation. Now, here the moment you subtract this from this, what do you get? For this entire quantity, what do you get? R x x k plus m minus r, isn't it? What? Not visible, okay. And you see, this entire summation is r and m. So, when you complete the summation, there is no r, there is no m. So, entire thing is a function of k only, isn't it? This is h r, h star m, and k and m and r. So, when you complete your summation, means just m and r are no longer present, they are local variables. So, entire thing is a function of k only, which means output also autocorrelation also depends only on the lag or the gap variable, that is k. So, I can write this RYYK, which means output is stationary, both in mean and in autocorrelation, which means output is WSS, wide sense stationary. Immediately then the question comes, oh, it is WSS. So, its autocorrelation function is actually a sequence of one variable only, k. If that be so, what is the corresponding DTFT? Because I can take, remember one thing, I can take power spectral density only for stationary processes, because only for stationary process autocorrelation function is a function of only one variable k. So, it becomes a sequence of one variable, and therefore, I can take its DTFT. If it is not stationary, the question of DTFT has no meaning there. Okay. Power spectral density applies strictly to stationary processes, WSS processes. Okay. So, now it is established that output also WSS. So, obviously, I may be tempted to find out the output power spectral density to see what it is. Okay. And I will try to relate output power spectral density with input power spectral density. So, starting from this expression, I want to find out this quantity. You can see this is RYYK, this summation is R y y k. Okay. So, I want to find out phi y y. Earlier I did not use the index, I simply said phi e to the power j omega, but the moment you have got different processes, I told you that I will bring in the subscript either x x or y y, not only for autocorrelation, also for power spectral density, because after all what is power spectral density? It is coming from autocorrelation. So, if autocorrelation has x x, this also should have x x. If y y, this also should have y y. If x y, there is a cross power spectral density x y here. So, phi y y e to the power j omega is this R y y k and R y y k, this huge expression we have found out. I have no other choice but to have to replace this R y k by this huge expression. So, it will become a triple summation. H r R x x and this good old fellow e to the power minus j omega k. Up till this your R y y k, up till this by the formula R y y k. This much only I have brought it down. The two summations are split. H only had R, so summation across R comes across, comes over H R, H star m, sum over m goes there. There is no point in having a sum over m before H of R, because H R does not depend on m. So, I push that inside. Okay. Now, I tell you there is a rule of thumb in DSP that whenever you come across double summation or triple summation, the next step should be interchanging the summation. If for double summation, then it is very simple, just interchange the two, again results will start follow. Okay, following. But in this case, there is triple, some interchange will be required. You bring in this one from outer to innermost, because H r does not depend on k, H star m does not depend on k. This fellow only depends on k, R x x k plus m minus r. So, bring this summation over k from outermost to the innermost one. Okay. If you do that, now, it is by j omega k. Okay. Just see this here please. It was k, but suppose instead of k I call it k plus m minus r. So, that these two indices are same. So, I have to have them cancelled. So, I should have e to the power plus j omega m, that depends only on m. So, I can put it here, and another term will e to the power minus j omega r. So, that depends only on r, I can put that here, and this quantity for your particular choice of r and m from outside, this quantity then becomes depending only on k, you are moving k from minus infinity to infinity, you can call this k prime, isn't it? For any choice of r and m, the r and m is fixed inside, and then k is only varying from minus infinity to infinity. So, k plus some constant, you can call it k prime. So, as k changes from minus infinity to infinity, so does k prime from minus infinity to infinity. So, R x x k prime e to the power minus j omega k prime. So, what is this quantity? This is nothing but phi x x e to the power j omega. What is this quantity? This is the DTFT of H n. So, this is capital H, and what is this? If you take the conjugate out, if you put it here and take this out and conjugate. So, this is H star, that means the entire thing is everything is what? Mod okay. So, mod h e to the power j omega, that is a real quantity. isn't it? So, real and real, so output is real, output PSD. So, you see this gives an idea about filtering. Suppose input process was white, okay. You want the output random process to have its power in the frequency domain localized around some zones and not present in other zones. So, you can design a filter with appropriate transfer function and that will shape the output PSD. That is the idea of filtering. You see, the filtering here is more general than the deterministic filtering which you are familiar in normal signal processing courses, low pass filter, high pass filter, because those are all meant for deterministic signals. Deterministic signal means signal is either having this frequency or those frequency, and so okay, I remove this frequency and pass. But when it is random, okay, it is fluctuating. In that case, I have to see power and only in a random from the stochastic point of view. Okay, this power spectral density, not instantaneous power. I have to find out average power. How? By integrating a quantity called power spectral density, that is the average power. That has meaning when for random processes, instantaneous power has no meaning. It is not a sine omega t as a sine omega t, its RMS power is a square by 2, it is not, isn't it? It is a random process, okay. It does not have a deterministic power. Every time the observation is changing. So, only thing that matters to me is if it is stationary, assuming stationarity, average power for any sample, and that is integral of a quantity called power spectral density. That will give you distribution of the average power across various frequencies. So, you want the output power to be localized in certain zone and gone elsewhere. So, you can boost up power in those components and elsewhere you can make 0. So, some kind of filtering will come up by your choice of h to the power j omega. Okay. So, this is not designed with respect to a particular deterministic signal in mind. There is a random process in mind and its average power in mind rather. Are you following this? The average power in mind, not instantaneous power of a particular sinusoid or particular signal. Okay. Average power of a stationary random process. I want to change its distribution in the frequency domain, how that power is distributed. So, signal will be called low pass if that average power, when you see its power spectral density, it is localized around origin, average power. Because average powers means what? This power spectral density when integrated gives you average power. I am always repeating average power, that has this kind of distribution. Then that will be called low pass random signal. Similarly, band pass standard signal and high pass standard signal and all that. Okay.
Sir, if it is not stationary, I mean it is not WSS, say the autocorrelation function depends on 2-time instant, still you can do the 2-dimensional DFT.
No, that won't have that meaning. You can have this called time, but then you have to have these are more generalized things. Time varying power spectral density, you can assume that to be constant, that you can assume this autocorrelation function initially to be a function of n and k, and that will not vary over n, piecewise stationary kind of thing, you know. It will be a function of two variables, they will call time varying spectral density and all. So, that will not have this meaning. You can try yourself to apply the argument there. It is not like an image signal, that okay, for an image signal, okay, I agree, it is a function of two variables and therefore, omega 1, omega 2 will come and all that, that thing will not come up, that meaning will go. Signal is one dimensional. Okay. Anyway, see one thing then very quickly, just for the case of say a real process, suppose I am dealing with a real valued process. For a real valued process, we know power spectral density is symmetric around origin. I am just proving something in a very using some simple steps, but to prove the result in a more general case, we will look at some further steps which I will avoid here. This I am trying to prove that power spectral density is non-negative. So, for that I am doing for the time being for real valued process, for which PSD is a symmetric function of omega. Okay. So, suppose you want to prove you are in this zone from minus pi to pi, you want to prove that phi e to the power j omega at any particular omega within the range, say maybe omega naught where omega naught could be any frequency. This is real, we know. We have to prove that this is this. This for any omega naught is, this is what we have to prove. For any particular omega naught of your choice, prove this. What I will do then, this for the random process x, phi x x, you have to prove. What I do then, you have given me omega naught. So, around omega naught and over a slot infinitesimally thin of width d omega, I will construct a band pass filter, suppose of height 1. This also d omega. Call this system h e to the power j omega. Okay, this is a system, linear time inverse. Suppose your random process x n, I am passing through this process, this system. So, output is y n. Output is y n. So, what is output power spectral density? That will be mod h into this we have just now proved. We have just proved this, isn't it? Mod transfer function square into this. But look at this filter. Even though they are appearing wide here, they are infinitesimally thin. So, phi x x e to the power, and then what is then output power? Output power will be just integral of this. But integral means what? This right hand side has to be integrated. Right hand side is to integrate from minus pi to pi. But you see, even though omega varies from minus pi to pi, you have to consider only these zones around omega naught. There is an infinitesimally thin strip of width d omega. So, what is the area of, suppose your phi e to the power j omega is something like this, real, so it is symmetric. So, if you want to really multiply, if you want to multiply phi x x, suppose this is your, I am just plotting, suppose this is your phi x x e to the power j omega. You want to multiply the two and then integrate over this range. What will you do? If you multiply this function with this, so this part and this constant height 1 will be multiplied. So, you will basically get back this times d omega. So, area of this strip, similarly on this side. But suppose this is very thin. If it is very thin, then this will not be so long. It will be so thin that the strip area will be approximated as the value of phi function at the center point, say phi e to the power j omega naught into d omega. Very simple calculus, because this is so thin. Here I have made it wide, so you can see such a variation. But if it is infinitesimally thin, area will be phi e to the power j center frequency omega naught times the d omega approximately. Here also, because symmetric, so same value will come here. That is important. Same value phi e to the power j omega naught or phi e to the power minus j omega naught same, that will come. So, what will be the next thing? That will be approximately 1 by 2 pi into twice, because this and this twice phi x x, not d omega, say delta omega. D omega is we used under integral and all, delta omega. Fine. The same thing, because symmetric I took, therefore, the height here and here will be same. So, I am giving this proof based on that real case only, but it can be generalized to the complex case, that I will not do here. This is a quantity, but I have told you any variance is real and non-negative. So, this is greater than or equal to 0. So, obviously, this will be, this quantity also is greater than or equal to 0. Delta omega positive is just a constant. So, is 2 pi. Okay. So, this is the proof that power spectral density is indeed a real valued function. Okay, I think I have got another 10 or 15 minutes. So, let us do some more serious business now. Suppose I have got a
set of random variables. Like yesterday I said x, then xy, then xyz, then xyz dot 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 dot, single density, joint density, and all those things. Suppose I have got a set of random variables x1 to xp, 1 to p, say. They are random. It could be such that x1 could be the nth sample of a random process xn, x2 could be xn minus 1, x3 could be xn minus 2, so forth, so on and so as a special case. In general, let there be a vector x. My vectors are always underscored. Matrices are capital letter underscored. If you read books and papers, they are not underscored, they are bold faced, but I cannot go on spending, making it bold. That will be terrible. So, I use this underscore thing. Okay. So, suppose I have got a set of random variables, in general complex valued. Okay. And E of x is what? Is a vector. You can call it mu x vector. That will consist of what? E over this, dot dot dot, E over this. That is mu x1 up to mu xp. They are mean vector. Then you find out this. If you take this vector and take its conjugate transpose. What is conjugate transpose? Transpose and conjugate each element, that is called Hermitian transpose. So, for your sake, let me, okay, I am just, it seems you do not know Hermitian transpose, so just couple of minutes, I am showing something. Suppose in general a matrix A, m cross n matrix, complex valued. Okay. Then A, we say Hermitian. A Hermitian means you either can take transpose of this complex, the conjugate, or vice versa A conjugate transpose. Either way you will get the same thing. This is called Hermitian transposition. For real valued matrix, Hermitian transposition and simple transposition, they mean same. Okay. Another thing, you know this, if you have A into B, suppose A and B are such matrices, they can be multiplied with each other. If it is m cross n and this is n cross p, something like that. Okay. So, they are compatible for product. Suppose you want to do this, multiply and then take H, that means you can say A B first transpose then conjugate. I should put underscore everywhere. And then B transpose, A transpose conjugate, but conjugate of a product, you can, these two matrices are multiplying, so terms are multiplied and then added. Conjugate of that means you can apply the conjugate on each term and all that you can do this. So, this is nothing but B transpose conjugate times A transpose conjugate, which is B Hermitian, A Hermitian. So, what you know for transposition, the AB transpose is B transpose into A transpose, that gets easily generalized to Hermitian transposition. And a matrix A, it has to be a square matrix actually. If it so happens that A Hermitian is A, obviously it has to be a square matrix, m cross n becomes n cross m. So, they can be same if n and m are same. Okay, you transpose and conjugate, and if this turns out to be this is called Hermitian matrix or conjugate symmetric matrix. For the real case, it is simply symmetric matrix. You know, if you take a square matrix transpose and if you get the same thing, it has to be a symmetric matrix only. Do you know or not? Aij after transposition becomes Aji. If Aji and originally at the Aij goes to Jith position, where Aji is located. But if you still get back the same guy Aji, then Aij becomes Aji. Aij you are transferring to the j comma ith position, and originally that was Aji. So, if these two things are same, that is after transposing you find that okay, you are hitting by the same quantity, there is no change, that means Aji and Aij are same. that matrix is called symmetric, which is real Hermitian. Okay, real Hermitian.
This is called Hermitian matrix.
This is the key of this course, Hermitian matrix. This has plenty of properties. I was to begin these properties of this matrix,
Hermitian matrix.
we will deal with what is called autocorrelation matrices, which are Hermitian. It has got beautiful properties. Those properties have to establish, then I will go into this further. Okay. Hermitian.
That is conjugate or conjugate symmetric.
In the real case, it is simply symmetric. Okay.
This for this. Now, suppose I take this
Difference vector x minus mu x. You remember what was cross covariance? Two variables were there, x and y. So, you take x minus mu x, y minus mu y multiplied x minus mu x times y minus mu y star, then expected.
Suppose I take this vector and take its Hermitian transposition. Firstly, this is a column vector. First one is a column vector.
Second one is a transpose conjugate.
So, is a row vector and conjugate. Its shape will be like this: column vector followed by a row vector with conjugate. Isn't it? There is a shape. So, it will be a matrix of size P cross P, and we apply E over it.
This is my claim. This is called the covariance matrix, or sometimes we call it autocovariance matrix. Covariance matrix.
C matrix C, and you can write C P cross P
Just to indicate the size.
Why it is autocovariance? What is the nature of this matrix? You see, you take these terms. First one is dot 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 x minus mu x, say, sorry, this is x 1, say x k minus mu x k dot 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 x p minus mu x p,
Okay.
and this side is conjugate of that. And one general term you can say x m minus mu x m
Star. Okay.
So, see what is happening. You know this column vector into row vector product. Now, this term will multiply this, then the second term, third term, and all them, E over each of them, that will form the first row. You know this is very simple. Do you know this or not? You know this, isn't it? This will multiply each of the term and separate entries of the first row will be formed. What is the first term? This into itself, variance. This into itself, but this into itself means this into itself conjugate. There is a conjugate here. So, x minus mu, x 1 minus mu x 1 mod square E over that, E is coming from behind. Isn't it? So, that will be variance. What variance? That will be your R x 1 0. Then x 1 minus mu x 1 into x 2 minus mu x 2 star. That will be what? Covariance between x 1 and x 2. Yesterday I told between x and y. There is no x and y here. X 1 minus mu x 1 into next term is x 2 minus mu x 2 star. So, that is, and then E over that. There is a covariance between x 1 and x 2. Okay. I will not call it, let me call it C. C x 1 x 1 0 actually is a variance with itself. Taken out the mean, mod square of that, expected value is a variance. And then you have got C actually this bracket should go, though no point in putting a bracket here as mixing up between x 1 and x 1. So, already lag is 0, 1 to 1 is so no point in being a 0 there. Then C x 1 x 2, okay, dot 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 C x 1 x p, isn't it? These elements, then again next one will be C then C x2 x2, dot 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 C x p x1 dot 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 C x p x p. You understand this matrix is what is diagonal entries are variant. So, real non negative, other elements are complex, but remember one thing, C x1 x2 and x2 x1 they are conjugate of each other. Covariance between x and y or y and x are they conjugate of each other. Covariance between x and y, I told you, order is important, yesterday I told you. E of x minus mu x times y minus mu y star, that is between x and y, and between y and x, E of y minus mu y into x minus mu x star. This is the conjugate of the other one. That is what you are having here. In one case, this quantity into x2 minus mu x2 star, and in another case, x2 minus mu x2 into this quantity star. So, that means this conjugate this ijth element, say 1 2th element, 2 1th element, they are conjugate of each other. 1 and 3 element, 3 and 1 element conjugate of each other, like that, so on and so forth. In general, this is a conjugate symmetric matrix. That means this covariance matrix is a Hermitian matrix. That you have to do, you do not have to show really taking this thing, that okay, take xi and xj, C xi xj, and that is in the ijth position, and jith position means C xj xi, and they are conjugate of each other. That way you can show, but very smartly you can show this way, that what is C after all? E into isn't it? What is CH? Means this matrix is to be transposed, Hermitian transpose, conjugate transposed. But E over this, you take E of a matrix, then do conjugate transpose, or better do conjugate transpose, then apply E operator, you will get the same value. E will not give, E operator will not give different values. So, so you can apply the Hermitian operation inside this, inside the E operator. You understand this, na? You are applying E operator on a matrix. Matrix consists of random thing. You find out expected value, then take the Hermitian transpose, or better just take the Hermitian transpose, then apply E. You will get the same thing, isn't it? Say E of x and then conjugate is same as E of x conjugate, because E of x means x into p x, conjugate means p x is real. I told all this yesterday. X p x dx is the E of x. The basic physics is x p x dx. Say this is E of x. If you want to conjugate this kind of thing, if you want to conjugate, this conjugate will come only on x star, which is same as saying that I am taking the expected value of x star. So, expected value of x star or star of expected value of x, both are same. So, that will be also applicable there, because it is a conjugate symmetry thing. Na? So, here instead of taking Hermitian over this entire expected value of the matrix, Hermitian means transpose and conjugate. You first transpose, interchange the positions and conjugate and then take expectation, you will still get the same thing. I told you expected value of conjugate or conjugate of expected value are same. So, that means H operator can go inside, and H of any product of, I told you A, B are two matrices, not necessarily square, any general matrices, A, B, H is B, H, A, H. So, that means this into this H over that H, that will come, this H will come first, this is B, this is A, okay. This H over that another H, are you following me? And this guy H. So, you get back the same thing, isn't it? You get back C. So, C is a Hermitian matrix, remember. This is covariance, and particular case where all the means are 0, okay, then it will be autocorrelation matrix also. Then correlation, covariance are same. So, we stop here today. So, Thursday morning we continue from here. This matrix has got beautiful properties we have to discuss, because they are useful. Okay, that is all. Thank you.